Hello, okay. Hello everyone. Okay, now we move a little bit to a different platform that I've been using previously. Now you can see my face for the first time, I think, for some of you. Okay, hello again, and this is of the lecture. Now we are moving on to clip number 6 already. Okay, and from the last clip we finished talking about the modeling of linear programming under uncertainty based upon the idea of paper of George B. Danzig, and we have gave you various type of example based on his paper, and also we set up some of our own example to give you illustrate that why the resulting model of LP under uncertainty based on the idea of that things can lead to very large scale linear programming. And now the reason we have to use this platform is that because we cannot use the direct window G anymore, because we have to switch allow several page with this explanation. Okay, we might go back to the paper of Danzig again, and then we go to the original paper here. Okay, as I told you before that we're going to use two platforms to study the problem within this semester. The first platform is the easiest one that, and you all familiar, is we're using the Excel. Okay, and also with this link which open for all of you. Okay, as I told you that we already open this okay, for all of you to be able to access. Okay, for lecture 1 here, okay, open also. Okay, we're gonna move to load this file of large LP test, okay, .xlsx. Okay, and I already download this file and then open it right here. Okay, this is the test problem that we gonna try to use it. Okay, in this problem, okay, if you want the original model problem, you might look at the sheet number 3 here. Sheet number 3 is the original problem here. Okay, in this problem we have a 6 variable over here, decision variable x of 1, x of 2, x of 3, x of 4, x of 5, x of 6. Okay, and the number of constraints, we can scroll down here. This is C number, the number of constraints. Moving on down here. Okay, keep going, keep going, keep going, keep going, keep going. Is 12,000. Okay, it's a lot, 12,000 constraint and 6 decision variable according to x1 to x6. And the problem is that, okay, how come I come up with this variable? Okay, this is like A matrix. You see, A matrix is here. Okay, scan up to the row number 12,000. Okay, the vector x variable, this is the x transpose. Okay, I'll put it in here. Okay, okay, this is a vector x, and vector of u and v. Okay, certainly u and v, the amount, how large the vector depend on how many constraint, how many equation constraint here. Okay, so u and v have maybe what, 24, each have 12,000. Okay, for each of them have 12,000 variable. So altogether u and v have 24,000 variable. Okay, plus 6 original 6 variable. So in this problem you have 24,006 variable. Okay, and the right hand side is very interesting, all equal 10. All equal 10. So we can establish the language of mathematics in the spreadsheet format. Since this is the variable, I already set up this problem in the file over here. And you might want interest that how come I get this? Did I type this? No, I didn't type it. The generation of each of these constraint coefficients, okay, is coming from the first row here. Okay, this is one. If you double click it, you get this one. You have rounding the number. You have 1 plus uniform random variable times 1, and then comma 3 is mean that the accuracy you need 3-digit accuracy. So the first column here, okay, over here, okay, the first column over here. Okay, so you can see that this random is always changed once you make an execution, because it have a formula that generates the random variable every time. But the value that put it in here already the numerical value, so it's not gonna change. Okay, but this variable, okay, generated from the formula in this rule. Like in the first column, if you look at this and we understand about random uniform random variable, okay, it will be the value between 1 to 2, because it's the minimum value start from 1. You plus random uniform distribution and with the range of 1, so the variable the value can start from 1 and end up cannot be equal to 2, and whatever the number that you generate, you're gonna try to round it up to only 3-digit accuracy. Okay, this is the meaning. That's why you can see that the value here, okay, 1.021, this is the value for the first column. It's not gonna reach the 2 value. The maximum value can only 1.999. The minimum value also can be 0.000, or but it's rarely happen. Let's just no, the minimum value is 1. Can be 1.000, 3-digit over here. The same way for the second column here, okay, that correspond to the x sub 2. It can be for minimum value of 1, and then maybe I increase the size here so you can have access. Oh, sorry. So you can see the formula much better. Okay, this one, the minimum value is 1, and then the range is 1.5. Therefore, from the minimum of 1, okay, they will uniformly generate the uncertain data from 1 up to 2.5. Okay, not gonna reach 2.5 with the precision of 3-digit. Okay, so this one is for the second column based on formula. Okay, so for each of these has this formula. You might say that, oh, so this is a mathematical problem. It's a no application and all of this. I will give you an example. Suppose that this is a kind of product mix problem. Okay, you have 6 raw material. Okay, it's a liquid. Let's just say that is a raw material as a liquid, and you this is the formula here. Okay, the range of formula that you can mix all these 6 raw material all together to get a product. Okay, so when you mix it up, okay, there's some quality characteristic. In this case, it might be the humidities or other type of quality product quality that you can set up. With the standard type of, you want to maintain at 10. That's why all 10,000 scenario you consider that the quality level you want is 10, maybe humidity 10%. But this coefficient here, once you already allocate the proportion of each raw material, okay, the how many raw material of first raw material, second raw material, third raw material, the mixing up the amount, okay, and this is the per unit of humidity that generated based upon each amount of raw material, and it's an uncertain value here. within the range generated by the first row here in column from column G to column L in the first row. Suppose this is the uniform distribution of 6 random variables here. Okay. Therefore, and it's a liquid, as I told you. So it's not the discrete part. Okay. It's a continuous value of possibilities. Therefore, you can have an infinite number of combinations. Or you might say that, okay, based on the accuracy of approximation, okay, each of them, for example, the first one, for the raw material fund, you start from 1, end up at 2 with the 3 digit, okay, so you can have 1, 1.001, 1.002, 1.003, up to 1.999, okay. So how many possibilities here? You can estimate. So from 1 to 1.999, from 1.00. So you have 1,000 alternatives, right? Look at it, 1,000 alternatives. For second row, okay, you end up here certainly from 1 to 1.5. Okay, so 1.000 to 1.499. Okay, 1.499. Yeah, right. That's for the 3 digit. Okay, so you can say that it's a 1,500 combination. Okay, and this one is 1 to 0.8. Okay, 3 digit. So 1 to 1.799. Okay, 800 alternative. Okay, this one is also 1,200 alternative. Okay, so this one is 1,050 alternative. Okay, and the last one is 900 alternative. Okay. So all together, okay, you can see that the large number of solutions, it become a multi-million. Okay, very large number. But this one we already sampling all possibility to only 10,000 cases. Okay, we only use 12,000. I'm sorry, 12,000. So for the first equation, we can write it down in algebra form, like 1.602 x of 1 times x of 1 plus 2.224 times x of 2 plus 1.388 times x of 3 plus 1.416 times x of 4 plus 1.674 times x of 5 plus 1.269 times x of 6. Okay. With all of this, you expect that the total humidity generated is equal to approaching the 10 value, the 10%. This is the unit as a percentage of humidity. But with the uncertain coefficient here for all 10,000 scenarios, you can't expect that when you already allocate the value of x of 1 to x of 6, you got for all scenario, in every scenario, you're going to achieve 10%. It's going to be either over, under, or over. If it's under, the U value will play a major role for you. Okay? If it's over, it becomes V. Okay? Over here. U plus U minus V. Okay? And this one, A times X, we use a sum product, right? Sum product of the variable X, and with each constraint column, okay, the dot is working like a dot metric. And the resulting is the same as A times X. And you know that we add one more column is that you need to balance it with right hand side. The left hand side is A times X using the result from that column, plus U minus V. This is the allocation of U and V. So this one you have a constraint that this one, the left hand side, row by row, need to equal to the right hand side. And certainly the objective function, the C here, we use the sum product. I kind of skip a thing that you are familiar with the uses of solver to solve the spreadsheet model. Okay, if some of you not familiar, you have a hard time to follow up what this model is all about. Okay, first you have a sum product of G3 to L3. This one is this one. Okay, G3 is here. Okay, and with G4 here. Okay, that's the first term. G3 L2, G4 L4. So this is C1 x1 times x1 plus C sub 2 times x sub 2 plus C sub 3 times x sub 3 plus C sub 4 by x sub 4 C sub 5 plus C sub 5 times x sub 5 plus C sub 6 times x sub 6. Okay, so this is the original, and you might say that this is the expected cost per unit in case that if your cost element also in the uncertain data. Okay, so this is the expected cost coefficients. Okay, let's look at the remaining. This is a C transpose X plus over here. Okay, we sum it up, M6 to M12005, and then sum it up from N6 to the row N 12,005, and then each of this with this sum you multiply to M3, this one multiply to N3, and all of this divided by E4. Okay, let's look at E4 first. E4 is here. This is the number of scenario. As I told you, this is the last part is to find the average cost. Okay, based on number of scenario. This one you have divided by 10,000 because of the assumption of uniform distribution. Okay, each scenario are equally important. Okay, so it's divided by the number of scenario, and then you sum it up all together, sum of all U, sum of all V. Because for each G and H, we simplify the problem that for all scenarios, G per unit is per unit U is 1.5, and then for V is become 1.55. This is a constant. It's not rely on the function, just like what we wrote in the model, that sometimes U and V or even the cost per unit rely on the amount of uncertainty that can happen in the real world. Okay, and you need a very big data to be able to indicate or compute all of that. But this one we just simplify that for all U and for all V in this scenario, the cost per unit is the same. So with the summation G times U summation H times V, it's only simplify that you need to find all sum of U multiplied by cost per unit of U, okay, divided by total number of scenario, and the V is the same. Okay, that is a resulting of this this formulation. Okay, so this one, so sheet 3 represent the original problem which you don't have any solution, but this problem is already solved in sheet 1. Okay, how do I solve it? Because it means that spreadsheet have a tool for you to solve it, and as you will see that the total number of variable is what, 24,006 variable, and the number of constraint is 12,000, which is a very large scale problem. But as we all know that the existing software that can be used to solve this problem is you can use the solver and as a routine to solve it. And solver we already put in the model here. Okay, and you know that this problem is linear, so you use the tool we call the simplex LP, and we try to solve it. And they would say too many variable cells. Certainly you can't solve it because the problem is too large. The attached solver from the regular Excel program solve the problem maybe just only 100 variable, 100 constraint. Some of them have some unlimited constraint, but the decision variable have only cannot be more than 100. Okay, so you cannot use the regular solver to solve this, and this become a large scale problem. Okay, 10,000 unit of both constraint and variable. Okay, but this is already solved. So what tool did I use to solve this problem? Okay, first of all, you have to go back to your original Google search, okay, and you can type what we call Opensolver. Okay, we type Opensolver here, and it's an open source software. Okay, and then you can download and install the program here. You can click it here. It's open. It's not illegal here. Okay, now it's in the version what we call 2.9.4. Okay, you can install it here by referring to this link. Okay, and there will be available that you can download it. Okay, so you can download, open Windows zip, and you can read the instruction to download it. Once you download it, it's gonna appear here. But first you need to download this, the current version, which I didn't have the current version here, but I'm gonna move you to this one, that to take a look at the what I have in over here. Okay, for this PC. Okay, I'm look at the download here, the thing that once you download from that website, okay, you're gonna end up having something appear to you. I did it for a long time ago. It's an open source. We can take a look at what we call the Opensolver. Here we have here. I have the WinZip of the Opensolver of 2.9.0 over here. Okay, it's cost only around 3 megabyte, not a large scale. But once you install it, it's gonna move it here. But if you just download it, it's gonna normally gonna appear in the very first line. But this one I already downloaded a long time ago. Okay, so I did get the Opensolver here. Okay, where is it? Oh, it's down here. I download a lot, so the appearance here might be different from your computer. But once you download it, okay, you're gonna end up having an Opensolver. Where is it? I already found one over here. Yeah, the Opensolver linear win here. Okay, and you need to unzip it. Okay, so from here, okay, I'm gonna I don't have WinZip, but I can open it with what we call the Unraw Metro. Okay, so I just so the download file is a zip file. Okay, so you either use the allow, you can, if you have WinZip, you can open it. Okay, once you unzip it, it's gonna install in your some folder, default folder that you identify here. But once it's appear here, okay, you look at the file, the Excel file they call Opensolver here. Okay, Opensolver down here. Okay, just double click it. Just double click. I just double click it. Okay, and then you it's a attached macro routine. Okay, so you need to enable macro. Okay, and then you get this one, the Opensolver here. So the result over here is using, and you have model here. Okay, we already put the model in here as a default. Okay, you can learn from reading from the website, also the instruction how to put the data in here. Okay, and you have a solver engine that you can also select. Many solver engine can be select, both linear and non-linear case, but some of them you need to purchase it or make a special installation like Globi or some other software. Not all of them available here. Okay, but we use the default one, which is the open source, we call the CBC. And then once I finish putting the model in over here, I'm ready to solve it. But I already solved it. Okay, so we pass through several lectures. Okay, we come to this point that I would like to assign you the first assignment for the course is that, okay, you go back and study how to solve this model. Okay, you might use sheet 3 as an example. Put the problem into the model, okay, here, okay, and learn to solve it using here, and observe the behavior of your computer responding to solving this quite a large scale problem. Okay, and I'm sorry that there'll be some difference between sheet 1 and sheet 3, because sheet 1 was solved based on the original problem that only 10,000 scenario. But for sheet 3, I already add more. Scenario, extend to the 12,000 scenario. So in sheet 1, if you want to solve the problem, check the solution down here. You need to reset by, okay, reset the original value here of x here. Set it to 0. Okay, all of this will be all 0. You can see that the resulting, that the left hand side is not quite frankly equal to the right hand side. It's almost in every row because of the round off error of the value of x here. Okay, the problem of rounding off that the all computation in computer need to do it as a irrational number. No, not the rational number. Not the fractional number. Sorry. Okay, so there will be some round off error due to the finite number of digits that represent the number. Okay, and almost 10 in all of this. Okay, but this one is guarantee that resulting the optimum solution. Okay, based on the 10,000 scenario problem. Okay, so what I want you to do is that go to the website of Opensolver, learning how to use it. It's very easy because the problem already set it up. You just put it in. You can see that for the model. Okay, you say where is your objective evaluation cell, which is this one, E sub 3, and then where is your changing cell? Okay, this one in the yellow zone. Okay, all x variable allocation and all the allocation of u, possible u and v. And what is your constraint? The constraint is try to balance left hand side and right hand side all equal. And then once you already input the model, you'll be ready to solve it. Just click solve. But I'm not demonstrating the solving part for you because I want to observe the behavior of your computer to the problem. And then next time when you come and continue, and we might have some separate class discussion. Okay, it was you to tell me that what's going on when you study to solve it. Okay, that's the first assignment. Okay, learn to use this tool to solve this problem. And this problem follow the footstep of Danzig's paper, Linear Programming Under Uncertainty, but I formulated as a spreadsheet model. Okay, we're trying to use an open source which not violated any copyright law, okay, to solve this large scale problem and observe its behavior when solving under the Excel platform. Okay, that's the first assignment. My second assignment is that, okay, you might have different problem here that, okay, now you have a 12,000 scenario here. Okay, with this appear in sheet 3. Again, try to solve it using Opensolver. Okay, and I want you to observe that this is a situation that you might have increase the number of scenario, right? Based upon statistical sense that if you increase the sample size, your objective function here and the solution here need to converge it to the population value. Okay, so you have to observe the difference between the solution at when number of constraints 10,000, 12,000. Is there any difference, or is converged to a population value already? Okay, or If still not, the next question is how large it's going to be. Do we need to increase 15,000, 20,000, or maybe 10,000? Or no, not that, or 100,000? That reached 100,000 units. Can your computer be handle that large size of the problem? Okay. You have a limitation of the RAM on your computer, and with different person with different capacity of your computer, okay, for among your classmates, the maximum size that you can handle may be different. Okay, so what's going on when the problem size keep growing? Okay, at one point, the response from the software will reach what we call the uncomfort zone. Okay, you can see that if you have an easy problem, you have enough memory to handle the problem, you click and the result will come up immediately. Okay, very fast. But once the size of the problem keep increasing, it, the problem can still be solved, but you can see the behavior of the response is getting slower, up to the point that maybe the computer stop responding and you don't know what's going on. And then suppose that you leave it at night, then you woke up at night or wake up in the morning, you still found that, oh, you still couldn't figure out, or maybe your computer turned off with no reason. Okay, hopefully it doesn't affect your computer that much with that size of the problem. So the last assignment for this usage of the open source software is that, can you find the limitation of this type of problem? We certainly, you increase the number of or possible scenario, keep increasing it. Is there any point or one more, or maybe 12,000 already with your computer limitation? It already reached an uncomfort zone. Okay, I want you to report all of this that I told you. Okay, learn to use the software, study the model, and try to run it. Expand the problem as large as possible, and keep running it until your computer stop responding or have a very slow response, and you feel that it reached the limitation of your hardware. Okay, next time, okay, we will continue solving this problem, but we try to improve the efficiency of using, now we're using what we call the direct method to solve it, but there is an alternative that you can save time and can help you increase your efficiency to solve a much larger scale problem. Okay, so see you next time. Okay, at this moment, okay, we wrap it up here. Thank you.